Hello everyone, my name is Ajay Meddi. In this presentation, I am going to discuss about concept video of aerospace structures, and that is symmetrical bending. Although symmetrical bending is a special case of the bending of beams of attributary cross section, we shall investigate the former first so that the more complex general case may be more easily understood. Symmetrical bending arises in beams which have either singly or doubly symmetrical cross sections. Examples of both types are shown in figure. Suppose that a length of beam of rectangular cross section, say, is subjected to a pure sagging bending moment M applied in a vertical plane. We shall define this later as a negative bending moment. The length of the beam will bend into the shape showing in figure, in which the upper surface is concave and the lower convex. It can be seen that the upper longitudinal fibers of the beam are compressed while the lower fibers are stretched. It follows that, as in the case of the eraser, between these two extremes there are fibers that remain unchanged in length. In this figure showing that the symmetrical bending, double rectangular and double I section, single channel C section and T section. In this both, the axis of the line is lying in center of these sections. So that is called axis of symmetry. In this, when a load is applied on a beam, it undergoes a deform, and in the lower surface it is stretched, and in the upper surface it will compresses. In the upper surface it is in the tension, and the lower surface it is on the tensile. It will stretches more, and between upper surface and lower surface the line which is called neutral axis is constant. The direct stresses therefore varies through the depth of the beam, from compression in the upper fibers to tension in the lower. Clearly, the direct stress is 0 for the fibers that do not change in length. We have called the plane containing these fibers the neutral plane. The line of intersection of the neutral plane and any cross section of the beam is termed the neutral axis. The problem therefore is to determine the variation of direct stress through the depth of the beam, the values of the stresses, and subsequently to find the corresponding beam deflection. The problem therefore is to determine the variation of direct stress through the depth of the beam, the values of the stresses, and subsequently to find the corresponding beam deflection. Assumptions. The primary assumption made in determining the direct stress distribution produced by pure bending is that plane cross sections of the beam remain plane and normal to the longitudinal fibers of the beam after bending. Again, we saw this from the lines on the both sides of the eraser. We shall also assume that the material of the beam is linearly elastic, that is, it obeys Hooke's laws, and the material of the beam is homogeneous. Next, we are going to see the direct stress distribution in open sections. Consider a length of beam that is subjected to a pure sagging bending moment M applied in a vertical plane. The beam cross section has a vertical axis of symmetry. The bending moment will cause the length of the beam to bend in a similar manner so that a neutral plane will exist, which is as yet unknown distance y1 and y2 from the top and bottom of the beam respectively. Coordinates of all points in the beam are referred to axis OX, YZ, in which the O lies in the neutral plane of the beam. We shall now investigate the behavior of an elemental length delta Z of the beam formed by parallel sections MIN and PGQ, and also the fiber ST of cross sectional area delta A distance y above the neutral plane. Clearly, before bending takes place, MP is equal to IG is equal to ST is equal to NQ is equal to delta Z. VD is equal to rho or GTT plus U cos psi plus V sin psi. Also, since the shear strains are assumed to be negligible, becomes substitutes. In this equation, we are showing the various equations. In this diagram, they are showing the direct distribution of a open cross section. Consider a length of beam that is subjected to a pure sagging bending moment M applied in a vertical plane. The beam cross section has a vertical axis of symmetry as shown in figure. The bending moment will cause the length of beam to bend in a similar manner to that shown in figure, so that a neutral plane will exist which is yet unknown distance y1 and y2 from the top and bottom of the beam respectively. Coordinates of all points in the beam are referred to axes O, X, Y, Z, in which the origin O lies in the neutral plane of the beam. We shall now investigate the behavior of an elemental length delta Z of the beam formed by parallel sections MIN and PGQ, and also fiber ST of cross sectional area delta A distance y above the neutral plane clearly before bending takes place. MP is equal to IG is equal to ST. In the diagram is showing that whenever a load is applied on a beam, horizontal beam, it undergoes some deformation, yeah, right, and the upper part is undergoes the tension and the lower part occurs the compression, lower part occurs the tension and the upper part tends to compress. I mean, whenever a beam is stretched, the upper part is in the compressed region and the lower part is subjected to tensile strength, I mean, which is used to stretch the beam, yeah, right. This is the point. The primary assumptions made in the determining the direct stress distribution produced by pure bending is that plane cross section of the beam remain plane and normal to the longitudinal fibers of the beam after bending. Again, we saw this from the lines on the side of the eraser. We shall also assume that the material of the beam is linearly elastic, that is, it obeys Hooke's law, and that the materials of the beam is homogeneous. Airplane wing structures. Thanks for watching my presentation. Thank you.